This is Learning Assessment Problem 3.2. In this problem, we are to determine the node voltages in this circuit, and the problem-solving strategy will be that of nodal analysis. The three node voltages are indicated as V1, V2, and V3. The reference node has already been selected. We have 4 nodes in the circuit. There are no voltage sources. So we have the number of node voltage equations necessary will be 4 minus 1 for the reference is equal to 3. So we'll have to come up with 3 node voltage equations in order to solve for these 3 voltages. As you recall, the nodal analysis involves the use of Kirchhoff's current law at nodes, summing the currents, and solving that set of simultaneous equations. So first we'll label the positive current directions assumed at each of these nodes, which will enable us to write the proper Kirchhoff's current law for each one. So if we look at KCL at the node V1, and sum those currents flowing away from the node being positive, we have minus 4 milliamps plus V1 minus V2 divided by 2K plus V1 minus V3 divided by 1K is equal to 0. Now we can rearrange terms here. We'll have 1 over 2K plus 1 over 1K V1 minus 1 over 2K V2 minus 1 over 1K V3 is equal to 4 milliamps. Or simplifying, we have 3 halves over K V1 minus 1 over 2K V2 minus 1 over 1K V3 is equal to 4 milliamps. So this will be one node voltage equation. Similarly, if we do the KCL summation at V2, we will have V2 minus V1 divided by 2K plus V2 divided by 1K to the reference node plus V2 minus V3 divided by 4K is equal to 0. Or minus 1 over 2K V1 plus 1 over 2K plus 1 over 1K plus 1 over 4K V2 minus 1 over 4K V3 is equal to 0. And again, simplifying, we have minus 1 over 2K V1 plus 7 over 4K V2 minus 1 over 4K V3 is equal to 0. So that will be our second node voltage equation. Now we'll continue. We have one more node voltage equation to write, and that's KCL at V3. We have the 2 milliamp source plus V3 minus V2 divided by 4K plus V3 minus V1 divided by 1K is equal to 0. Simplifying, 1 over 1K V1 minus 1 over 4k V2 plus 1 over 4k plus 1 over 1k V3 is equal to minus 2 milliamps. And again, simplifying that a bit more, we have minus 1 over 1k V1 minus 1 over 4k V2 plus 5 over 4k V3 is equal to minus 2 milliamps. So that's our third node voltage equation. If we put these into the matrix format, we will have 3 over 2k minus 1 over 2k minus 1 over 1k minus 1 over 2k, 7 over 4k minus 1 over 4k minus 1 over 1k minus 1 over 4k and 5 over 4k. That's the conductance matrix times the voltages V1, V2, V3 is equal to 4 milliamps, 0, and minus 2 milliamps. Again, solving, we have V1 is equal to 5.4286 volts. V2 is equal to 2 volts. V3 is equal to 3.1429 volts. Continuing, we'll write the third KCL equation at the node V3. So we'll have the current source 2 milliamps plus V3 minus V2 divided by 4k plus V3 minus V1 divided by 1k divided by 1k is equal to 0. Rearranging terms, we have minus 1 over 1k V1 minus 1 over 4k V2 plus 1 over 4k plus 1 over 1k V3 is equal to minus 2 milliamps. And simplifying, we have minus 1 over 1k V1 minus 1 over 4k V2 plus 5 over 4k V3 is equal to minus 2 milliamps. So we can place this information that is our third node voltage equation. So we can place this information in the matrix format for these three node voltage equations. And we'll have 3 over 2k minus 1 over 2k minus 1 over 1k minus 1 over 2k, 7 over 4k minus 1 over 4k minus 1 over 1k minus 1 over 4k and 5 over 4k. That's the conductance matrix times the voltages V1, V2, V3 is equal to the currents 4 milliamps, 0 and minus 2 milliamps. So solving this by your favorite technique, you'll determine that V1 is equal to 5.4286 volts, V2 is equal to 2.0 volts, and V3 is equal to 3.1429 volts. So those are the three node voltage equations.